This is Mr. Richens, and welcome back to another lesson in chemistry. This lesson will be the first in Unit 4, and it's going to be about chemical bonding, Part 1. Three topics: valence electrons, Lewis structures, and finally, chemical bonding. Valence electrons are the electrons in the outermost s and p subshells of an element. Let's consider sodium. Its electron configuration is 1s2, 2s2, 2p6, 3s1. We can replace this part of its electron configuration with the electron configuration of neon. And so we can see that it has one electron in its outermost subshell, and that electron is the valence electron. If we consider another example, let's go ahead and consider selenium. It's a little bit more complicated. Its electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and finally 4p4. And we can replace this part of its electron configuration with the electron configuration of argon. And so its noble gas notation is argon, 4s2, 3d10, 4p4. Now the outermost s and p subshell is the 4. And so this is the valence electrons for selenium. D orbital electrons, d subshell electrons, can participate in bonding, but we're not going to be considering those in this course. Instead, we're going to be focusing on just those electrons in the s and p subshells. So, valence electrons. They are the electrons in the outermost s and p subshells, and they are the electrons that participate in chemical bonding. So, valence electrons, the electrons in the outermost s and p subshells, and the electrons that participate in chemical bonding. In order to represent those electrons, scientists, chemists, have developed a method of illustrating them called Lewis symbols. Lewis symbols represent those outermost electrons, those valence electrons, as dots around the symbol. So, for instance, sodium, it has a Lewis symbol of Na with a little dot. The single dot represents the valence electron. Magnesium would have two dots. Those two dots representing the two electrons in its outermost s subshell. Aluminum, 3 dots. Silicon, 4 dots. Now you'll notice that we've placed these dots on separate sides of the symbol because each of these 3 sides represent the p orbitals that the electrons go into. And so, following Hund's rule, we want to put 1 electron in each of them. If we go to phosphorus, we've got 3 electrons, 1 in each of the p subshells. And when we go to sulfur, we start pairing up the electrons, and we end up with 2 in this p orbital here, and lone electrons in the other p orbitals. If we go to chlorine, finally argon, like that. These Lewis symbols will allow us to illustrate how chemical bonding takes place, what happens to the electrons during chemical bonding. So, if we consider, let's look at another one. Let's go with calcium. Well, calcium is in the second column, which means that it has 2 electrons in its s subshell. So we just have to put 2 electrons like that. If we consider oxygen, oxygen is in the 4th column of the p block, and so that means it has 4 electrons in its p subshell. So it's got its full s orbital, and then it's got 4 electrons, and so there's oxygen's Lewis symbol. It has 2 in the s, and then 1 or 2 in the first p orbital, and then 1 in each of the other p orbitals. There are 3 types of chemical bonds that we're going to be interested in: ionic bonds, covalent bonds, and metallic bonds. As it turns out, between ionic and covalent, there is a gradation, a spectrum over which it occurs. Bonds aren't completely necessarily ionic or completely covalent. Instead, there can be aspects of both. But generally, this is what happens. In ionic bonding, electrons are transferred, and this typically occurs between a metal and a nonmetal. In covalent bonding, electrons are shared, and this usually occurs between nonmetals. In metallic bonding, what you have is a group of metal cations surrounded and mutually attracted to a sea of delocalized electrons. Those delocalized electrons come from the valence electrons, and they're shared among all the different cations. And so you'd have like iron 3 ions, cation, all in the metal. And then around it, all around it, you'd have all these delocalized electrons floating around, being attracted to all of them, and each of them simultaneously. That's all I want to say about metallic bonding. Tomorrow, we'll be talking more extensively about ionic and covalent bonding. See you then.